Hey everyone, welcome back to Control System Lectures. This is the second video on discrete control, and in this one I want to focus on discretizing a continuous system. Now, if you recall from the last video, I mentioned 3 ways to design a digital controller that will run with a continuous plant, and 2 of those ways require converting systems between the S and Z domain. Let's recap with a flowchart. We have a continuous plant for which we need to design a discrete controller. Now we could design the controller in the continuous domain, then discretize it, and end up with a discrete controller that we hope is equivalent enough. Or we could discretize the continuous plant at the beginning, and end up with a discrete plant that we hope is equivalent enough to design a discrete controller against. In both of these cases, we are taking a continuous system and discretizing it. In the first case, we're discretizing the controller, and in the second case, we're discretizing the plant. But the method is going to be the same for both of them. So let's talk a little bit about how we do that discretization. Specifically, we're going to focus on going from a continuous system to an equivalent discrete system. Your first thought might be, isn't there that Z-transform thing? Can't we just use that and be done with it? Well, the Z-transform is part of the story, but it's not the whole story. To understand why, let's first think about the continuous system and the Laplace transform. Recall that a continuous linear time invariant transfer function is the Laplace transform of the impulse response of a system. That is, take an LTI system, find its impulse response, and you can do that either with testing or by writing out the equations of motion, and then take the Laplace transform of the resulting signal or equation. Since it's LTI, we can now subject that system to an arbitrary input signal that's also represented in the S domain, and then the output of the system is simply the product of the two. That multiplication is one of the benefits of going to the S domain. We don't have to mess around with convolution. So now let's think about how we would approach discretizing this problem. Or basically, how do we get a transfer function that is discrete and represented in the Z domain rather than continuous and in the S domain? The first part of the problem is the same. We have our same continuous LTI system and we find the impulse response. But now we can discretize it by sampling the time domain impulse response at whatever sampling period t we want. That just means we're grabbing a value every t seconds rather than keeping the entire continuous information. We're left with a discrete sequence of numbers, g sub k. And from here we can now take the z transform of g sub k to convert our discrete time domain signal into a discrete z domain signal. This results in a discrete transfer function that, just like with our S domain counterpart, represents the impulse dynamics of our discrete system. For this example, I've assumed a sample time of t equals 1 second. And this is still an LTI system, and multiplication in the Z domain is the same as convolution in the time domain. So just like with the S domain transfer function, we can just apply arbitrary inputs, and the response, once again, is the product of the two. If the system we just converted was a controller we designed, then we can think of the input as a sequence of discrete set points, maybe a set of desired motor speeds, and the output would be a discrete actuator command, like a new voltage command to get to that motor speed at every sample time. Now this seems all really logical, right? We just sample our time domain signal and then convert it to the Z domain with the Z transform. But there's a slight problem with this method that we need to discuss. And in order to understand what that problem is, we should probably work through an example by hand. Let's say we designed a continuous controller that just happened to be the very simple g of s equals 1 over s plus 1. We can get back to the time domain g of t using the inverse Laplace transform, which gives us g of t equals e to the minus t. Now I could get that by solving the inverse Laplace transform itself, or as I just did, look it up in a table of already solved transform pairs. So what we've just found is that if our system transfer function is described by 1 over s plus 1, then the impulse response of our system is a signal that starts at 1 and then exponentially decays. So if you hit it with an impulse, this is the time domain response. Now, to find the Z-domain equivalent for this, we first sample it at some fixed period t to get a sequence of numbers, g of k equals e to the minus k times t, where k is an integer that represents the sample number. Then we can take the Z-transform of that sequence of numbers to get g of z equals z over z minus e to the minus t. which again, I just went to a z-transform lookup table to find it. I didn't solve this one by hand right now. For this example, let's set t to 0.1 seconds so that the z-transfer function becomes z over z minus 0.9048. And this is the z-domain representation of our system's impulse response when sampled at 0.1 seconds. We should remember this because we're going to reference it later. So that's a way to go from an S-domain system to a Z-domain system. But come on, why are we doing this by hand? This is 2007. Well, it depends on when you're watching this, but the point is we're not going to solve inverse Laplace transforms and Z-transforms by hand. We're not even going to look them up in a table. We're going to understand the concepts, we're going to understand the math behind it, and then we're going to do a few examples by hand to get a good knowledge foundation, but then we're going to turn to the computer and solve future discretization problems with a program like MATLAB. So let's go do that and see what we get. So over in MATLAB, we're going to start by creating the continuous transfer function g equals 1 over s plus 1. I'll set the sample time ts to 0.1 seconds like our problem. Now, the discretization problem in MATLAB is done with the function c to d. This stands for continuous to discrete, which is pretty straightforward naming, so this should be pretty easy. However, our problems start when you look at the help file for c to d and realize that there are 5 different discretization methods to choose from, and none of them say use the z-transform method. The options are zero-order hold, first-order hold, impulse, Tustin, and matched. And the default method, if you don't supply one, is zero-order hold. Okay, well, let's just try them all and see what the differences are. I'll start with the zero-order hold method and assign gz, the result of the c to d function for input system g with sample time ts and the method zero-order hold. Now already gz looks close, but not exactly like what we created by hand because there's no zero in this transfer function. Now using this same structure, I'll quickly zip through the remaining 4 methods and call the resulting functions gf, gi, gt, and gm for first-order hold, impulse, Tustin, and matched respectively. So now let's go back to the blackboard and I'll rewrite them so that we can compare them to each other. And we can see that they're mostly different from each other. Now the characteristic equation is the same, which means they all have the same poles and therefore the same stability, but the zeros are all over the map. And worse than that, none of them match the z-transform method we just did by hand. I mean, the impulse method is the closest, but it's off by a gain of 0.1. Now we'll come back to that in a second. But first, let's go back to MATLAB and plot the step responses and bode plots for each of these representations. The bode command allows you to plot several systems at once if you offset them with commas. And then just for clarity, I'll add a legend so we can tell which response goes with which system. However, the exact response isn't important for what I'm trying to show you, so don't try to squint at the screen too much to see what's going on here. Now I'll do the same thing for the step response as well. And as you would expect from different transfer functions, they have different responses in the time and frequency domains. Alright, so what gives here? I mean, how do you choose the right method? How are they actually different, and why don't they match our hand calculations? First off, the method you choose depends on what you're trying to accomplish. When we convert from a continuous to a discrete system, we necessarily lose information. We're sampling a continuous system and only looking at some of the data. Our job is to figure out what is important to us and then minimize the loss in that area. For example, we may care very deeply that the frequency response of the discrete system matches the frequency response of the continuous system, but we don't care as much that the time response of the two systems are different. This is the case with notch filter design, for example. Or we may want our discrete system to represent the time response to a step input really well, but we don't care if the cutoff frequency moves around a bit. Each discretization method has its benefits depending on what you're trying to do, and they will lead to slightly different discrete representations of the same continuous system. That's why there's so many methods to choose from. And we'll step through 2 of them in detail and then discuss the others a little bit to show their strengths and weaknesses. But before we get bogged down too far into the mathematics of all of this, let me start by saying that all of these methods produce nearly the exact same time and frequency responses if the sample time t is short enough. That is, if the dynamics, or the time constant of your continuous system is relatively slow compared to the sample time, then it doesn't really matter what method you choose. They're all about equivalent. So let's go back to MATLAB and change the sample time from 0.1 seconds to 0.005 seconds and then recalculate each of our discrete systems. Now when we check the bode plot and the step plots, the results are much similar. The frequency response matches much better up to a higher frequency, and the time responses are almost exactly the same. So if you're worried about all of this discretization stuff, just make sure that the computer you're running your control law on and your digital sensor rates are sufficiently fast, and your digital system will behave like a continuous system. But again, this isn't always possible because of what I said in the last video, that faster sample times make the engineering harder in other areas. So it's worth diving a little bit deeper into each of these methods. We'll begin with the impulse method, or as MATLAB refers to it, the impulse invariant method. This method's claim to fame is that it produces a discrete time model with the same impulse response as the continuous system. That is, the impulse response does not change or is invariant between the continuous and discrete domains. To see that this is true, let's go back to MATLAB and set the sample time back to 0.1 seconds to once again accentuate the differences between the discretization methods. Then we can compare the impulse response between the impulse invariant method, the continuous system, and, say, the zero-order hold method. We can see that the impulse method matches the continuous result perfectly at the sample points, whereas the zero-order hold method is clearly different. There's a lag there. What might be confusing is that the z-transform method we did by hand was supposed to represent the impulse response of the function, right? I mean, we took the z-transform of the discretized impulse response. Therefore, wouldn't you expect if we just went in the opposite direction, that is, from the z-domain back to the time domain, it would just produce a sequence of numbers that perfectly lie back on the impulse response curve? That is, wouldn't you think the impulse invariant method in MATLAB is equivalent to just sampling the time signal and taking the z-transform? Well, it actually is. Remember, this is the method that got us the closest to the z-transform we did by hand. In fact, they're only off from each other by a factor of 0.1, which just so happens to be the sample time. You'll find the answer to why the answer is scaled by the sample time if you look at how MATLAB defines an impulse. The impulse command in MATLAB computes the response to a unit area pulse of length ts and height 1 over ts. For our sample time of 0.1 seconds, the width is 0.1, and so the height is 10, such that the area under the pulse is 1, or a unit pulse. This contrasts with the definition of the Kronecker delta, which is used as the definition of the impulse in the z-transform tables, where the value is 1 for the first sample and 0 for all other samples. Therefore, our MATLAB z-transform is scaled by ts, but only because of the way that the impulse is defined. So to get back to the hand z-transform method, all we have to do is divide the MATLAB result by ts. Now this seems like a pretty great conversion method, right? It's analogous to what we do with the Laplace transform in the continuous domain, and so there's some similarity there, which is nice. And if your input into the discrete system is a series of impulses, which is also called an impulse train, then the discrete response would behave as you expect it to. Unfortunately, an impulse train is not usually the discrete input when you're dealing with a system that is interacting with a continuous system. Typically, the discrete input is not treated as an impulse, but a step. That's because when you get a single measurement or you issue a single command to an actuator, you hold that value constant until the next sample period. For example, if you're trying to control a motor and a digital computer is sending the motor speed commands once a second, you don't let the motor spin down in between commands as you would with an impulse. You would hold the wheel speed command for the full second until you got another command, and then you would update it. This type of staircase input is accomplished with a discrete to continuous method called a zero-order hold. That is, hold the previous value with zero slope, or a zeroth order polynomial, and step up the value at the next sample time. This results in a series of small step functions and not a series of impulses. If we go back to MATLAB and check the step response for the impulse invariant method, you'll see that it does not match the time domain response very well. And that's not ideal. If we use this method to discretize our system, but then subject our system to a series of step inputs, we won't have the behavior we want. But if we compare the continuous system with the zero-order hold method, that does compare well. In fact, because of this, another name for the zero-order hold method is the step invariant method. So for systems where the discrete values are held constant between samples, we would want to use the zero-order hold method so that the staircase input produces an exact match between the discrete and continuous time domain systems. Or to tie it back to our controller design, we want our discretized controller to behave like our continuous controller when subjected to the same types of inputs. And in our case, our inputs are not impulses, but step functions that are generated by a zero-order hold. Therefore, we want our discretization method to include the effects of that zero-order hold, as well as discretizing our system. Now, to understand how this method works and what the function is doing under the hood, let's work through the math by hand. Now, I know we said we would just use MATLAB in the future to discretize systems, but only after we have that good knowledge foundation. And I don't think we can responsibly claim that we have that foundation unless we've worked through the math behind it at least once. Now, in order to understand some of the mathematical steps we'll take in this derivation, we need to start with some definitions. The variable z is equal to e to the t times s, where t is the sample time of the discrete system, and s is just the complex variable that you're already familiar with from the Laplace transform. And then the z transform is the summation over all positive integers k of the sequence f of k times z to the minus k. For the moment, don't be too concerned with the specifics of these definitions. I'll cover both of these in a future video on the z-plane and the z-transform. Right now, just know that the variable z is related to the variable s, and that the z-transform converts a time-domain discrete signal into a z-domain discrete signal. Alright, with these definitions we can look at the zero-order hold and how it affects the discretized system. Let's start with the block diagram. On the far left we have our discrete sequence of numbers, vk. This is in the time domain and it's the input into our system. Again, this could be discrete measurements from a digital sensor like a temperature reading every second, or it could be the discrete commands to an actuator like our motor speed commands from earlier. We send those discrete values through a zero-order hold to convert them to a continuous time signal, v of t. This continuous time signal is fed into our continuous plant, g of s, which has the continuous output, y of s. Finally, we sample y of s at some sample time, t, to get the discrete output, y of z. With this block diagram, it's easy to see that we are trying to represent the zero-order hold, the plant g of s, and the sampler all together as a z-domain transfer function. So let's start with figuring out how to represent the zero-order hold as a function. The input signal vk has a value every t seconds. Now after the zero-order hold, it looks like a staircase with one stair or a pulse every t seconds. Let's look at an arbitrary pulse k somewhere in the middle of the signal. The pulse starts at time k times t and ends one sample time later at k plus 1 times t. Also, the height is constant the entire time with a value of vk for that sample number. Now we can create this pulse with the summation of two step functions, a positive step function at time kt and a negative step function at time k plus 1 times t. Here, the capital fancy U represents the unit step function, such that in the blue equation, u of t minus k times capital T is just a step function that's delayed by time kt. And in the green equation, it's a step function that's delayed by time k plus 1 times t. So that the single pulse at index k is just the summation of those two. But this is just a single pulse. We can get the entire signal by summing across all k. So pulse by pulse by pulse, we're adding and subtracting two step functions. And through this method, we've converted the discrete signal vk into a continuous signal v of t. Look, we're already making some progress. But this is a time domain signal, and if we want to combine it with our plant, g of s, we need to put them both in the same domain. Therefore, we can take the Laplace transform of v of t to convert it into the s domain. Now recall that the Laplace transform of a step function at time 0 is simply 1 over s. And if the step function is delayed by time t, then the Laplace transform is 1 over s times e to the negative ts. So that the Laplace transform of v of t is as follows. Now the e's raised to some power make it look more complicated than it really is. but in the blue equation, it's still clearly just two delayed step functions subtracted from each other and then scaled by the height vk. We can leave it like that, but we're going to rearrange it into the pink equation for reasons that I think will be obvious in just a bit. We now have the S-domain representation of a zero-order hold acting on the discrete signal vk. Now if we go back up to our block diagram, you can see that we have this signal v of t, but represented in the S-domain. And this is an important step because what we really want is the output y of s. And since we have v in the S-domain and g in the S-domain, we can simply multiply them to get the output. We can then factor out the terms without k out of the summation block to get this peach color equation. At this point, we can finally use the definition for variable z that we started with to simplify this function. We're left with y of s, or the continuous domain output of our plant, equals 1 minus z inverse over s times g of s, and then that quantity multiplied by this summation. Now this is where I hope rearranging our equation earlier made things obvious. It made it clear that this summation is just the z transform of the discrete signal vk. That is, the summation is converting vk to its z-domain equivalent, v of z. If we make that substitution and do a little rearranging of the 1 minus z inverse, we are left with the transfer function from the input signal vz to the output signal y of s. And we are so close at this point. Now we can't actually multiply these two quantities together because they're represented in different domains. Therefore, we can take the z transform of the terms with s in them so that they're all in the z-domain. Now, the way to read this final equation is to start with your continuous plant, g of s, divide it by s, which is essentially integrating it, convert that s-domain system into a z-domain system by sampling the time domain equivalent and taking the z transform, and then multiply that whole thing by z minus 1 over z. The end result is the z-domain representation of your continuous system and the zero-order hold. Now this might require you to pause here and review the math at a little slower pace. And if you do that, you'll realize that I made a small mistake in the equation in the yellow box. The left side of the equation should be y of z over v of z, and not y of s over v of z. But once you finish reviewing the math, let's go through a quick example with our g of s from earlier. First, we divide g of s by s to get 1 over s times s plus 1, and then sample at 0.1 seconds and take the z transform. Once again, I just looked this up in a table to get z times 1 minus e to the negative t over z minus 1 times z minus e to the negative t. We then evaluate that at t equals 0.1 to get 0.09516 times z all over z minus 1 times z minus 0.9048. We can then multiply by z minus 1 over z, make the appropriate cancellations, and what we're left with is 0.09516 over z minus 0.9048. This is our equivalent zero-order hold discrete transfer function. And the important part is that it matches exactly what MATLAB produced. Now the zero-order hold method is important because, like I said earlier, it's a very common way for discrete systems to interact with continuous systems. We just hold that discrete value constant until the next sample time. That is why this is the default method in MATLAB, and not something like the impulse invariant method. Now, I said I'd briefly describe the other three methods at the end of this video, but it's starting to get a bit long, and I don't really want to rush through them. Therefore, I'll cover first order hold, Tustin, and matched methods in the next video. Don't forget to subscribe so you don't miss those future videos, and thanks for watching. And a huge thank you to my Patreon supporters for making this video possible. If you'd like to support me and my efforts on YouTube, you can from the Patreon link in the description below. For any amount of support, you can download a digital copy of my book, In Progress on Control Theory. Now, I'm still actively writing the book, so it's not complete, but if you would like a copy of what I have so far, and you don't want to support me through Patreon, just email me at controlsystemlectures@gmail.com, and I'll just send you a copy for free. That way we can spread the knowledge and help everyone on their quest to becoming better control system engineers. Thanks, everyone.